that 10 bar these glasses same back. It's a special refrigerant for that. But it still demonstrates the purpose. Visually is why we're doing it. What we have here is this refrigerant water that's a vacuum. You know that when you go into a mountain you can boil at a lower temperature. Well, it's the same thing because in a deep vacuum this water is boiling and it's boiling out about 10 degrees, 9 to 10 degrees. So we've got water going through there. Water is the heat source. So although the water is at 10 degrees C, the refrigerant 5 is at 4 degrees C. So that water is giving 5 degrees of heat into the refrigerant and making it boil. Yeah? Turning it into a vapour. The vapour comes out of the pipe at the top. Yeah? Into the compressor. Compressor compresses it up. We have another temperature here, and you look on your chart, you can see the ones we're looking at. It's actually 5, 6, 7, and 8. Yeah? 5, 6, 7, and 8. Those are the ones that are about the fridge plan. Again, we can do the same overall balance system with that if we wanted to. We can work out the flow rates. We can work out the flow rates, the temperature difference of the water. Yeah? MCP delta T. Yeah? CP of water 4.2. Yeah? Mass flow rate, temperature difference. We can work out how many kilowatts. But in order to get the visual effect of this boiler, I've got a lot of water going through. So there's next to no temperature difference in that. Okay? I've got a lot of water going through. If I were to reduce the water, then you wouldn't see the visual effect of the boiler. So it compresses it. It's now hot. Yeah? Hot and sweaty. Yeah? So hot and sweaty gas. We have 10 degrees C of water again going in the coil. So the sweaty gas, this gas that's hot, is condensing on the pipe and dripping off. This bit at the bottom here is the expansion valve. It's called a floating expansion valve. The main idea of an expansion valve, take the term away expansion valve, it's a valve that makes pressure difference from here to here. So here we're at high pressure, here we're at low pressure, and that balance is just keeps stopping the pressure going through all the time. We get a large build-up of refrigerant, it lifts it, and lets more through, yeah? And then it drops and closes the valve. There is flash gas going on, I'm not going to go into that, it's far too technical. So, exactly the same as the other system. We're going to turn around, two pressure readings, 0 and minus 70, 80, yeah? But it says on here, this is in kilonewtons per metre squared, and it says on the gauge that 100 kilonewtons per metre squared is equal to 1 bar. So 0.1, yeah, of a kilonewton, yeah, is equal to 1 bar. Yeah? So the gauge is actually very easy to read. Yeah? But make sure you've got that in your head. So in essence, this is gauge pressure, this is absolute. So when we have 0 there, we have a 1 here. Yeah? Because we're minus 0.8 there, we're actually up 0.2. We're up 0.2. Make sense? Yeah? Okay? Equivalently, if we were down minus 0.1, yeah, or minus 10, realistically, it would be 90, wouldn't it? Yeah? Right? Because it's up. There you go, on that scale, up here. Right? Same with that pressure there at 0, which is 1 bar. Going 2 lines across. The temperatures you need is the cold temperature, which is the lower temperature, which is this point here. Yeah? And that is in the evaporator, that's 5. That's where we're going now, which is at 4 degrees C. You're exactly the same. We're at 0.2. It's telling me I'm actually boiling about minus 8. Yeah? So if we're actually at 4, we take the temperature reading 4 and draw the line down about there. Look at the bit where it comes out of here, which is the compressor, which is 7. .74-ish. We look at what we say at 0, which is 1 bar, and that says about 30 degrees, 32 degrees-ish. we come across here, we find a temperature of 70, which is up there somewhere. We draw a line down and meet that horizontal line. Point 1, point 2. The last one we need is the liquid. Which again is 13 degrees C. So one bar, we're actually come right the way across to here. Really well subcooled. Draw the line until it meets them. And that line will also come down here. So you've now got your chart. Extrapolate down here, and here. Look at the difference here, the difference there. Okay? Where your cop out, that goes into that so many times. Cop HP, that goes into that one more, obviously. The only other thing we can do with this, we don't have refrigerant flow. Right? Something of interest, if you want to play with it and put it around it. We have the watt meter of the compressor. It's taking 250 watts. Right, with that system, by looking at the units at the bottom, kilojoules per kilogram flow, we multiply it by kilogram flow, we end up with watts. If we know the watts, we can work out the kilogram flow. Yeah? Just by the reverse process of what you're doing there. That makes sense? Are you happy? I'll be hanging around if any questions. If you want to, half you go on that one, and half you go on this one. Yeah?